Hi everyone, it's Rajiv Ramchand here again with session 4 in this basic epidemiology series to help provide you with some basic information to understand this pandemic, this COVID-19 pandemic that we're going through. So let's start. Today we're going to be talking about herd immunity, or this session I should say, we're going to be talking about herd immunity. And in all honesty, I borrowed a lot of this information from a really excellent research paper I found called Herd Immunity, A Rough Guide by Paul Fine, Ken Eames, and David Heyman. So the basic concept of herd immunity is that we can create in a population a pattern of immunity that should protect a population from invasion of a new infection. It really kind of, this concept of herd immunity really kind of accelerated with the development of something called the threshold theorem. I'm going to read it, but we're going to walk through it. And I promise if it's confusing to you as we walk through it, it will hopefully become less confusing. What it states is that if immunity were delivered at random, and if members of the population mixed at random, such that on average, each individual contacted are not individuals in a manner sufficient to transmit the infection, then incidence of the infection would decline if the proportion immune exceeded 1 - 1 over R naught. What the heck does that mean? Let's go through it. So let's assume that we have a person who enters a population and with an infection. And let's assume that this R naught, this concept of R naught that we just described, is 4. So that means that in the population, this new person comes into the population and infects 4 cases. Then those 4 individuals then have this infection, they're in the population, they in turn infect 4 additional individuals themselves who are susceptible. So we go from 1 case to 4 cases to 16 cases, and you see how this can just dramatically increase over time. What is this threshold theorem? What is 1 - 1 over R naught? Well, remember, R naught is 4, so 1 - 1 over 4 is 3 over 4, 3/4. So this threshold theorem that they're saying is that if we had immunity among 75% of this population, we had reached this threshold theorem. So what does that mean? So let's say this person encounters this woman and she has built up immunity. How many to the infection? How many transmissions will occur next from her? Well, 0, because she's immune to it. So, or she's developed the immunity to it. So she can't transmit it to anyone else. And those 4 people that she had seen, 3 of them were also vaccinated and 1 of them wasn't, because we're assuming this 3/4 of the population at this threshold level. But let's say he meets this woman and infection occurs. She is not yet immune to it. How many people will then she pass the infection onto? If you answered 1, you're correct, because remember, we're assuming 3/4 of the population is immune. That means 3/4 that she's interacting with. So she's not going to pass it to these 3 individuals who are colored in, but she will pass it on to this 1 person who is potentially not yet immune to the infection. So if we just kind of take that out, we have, or blow that up really, we have this 1 person who's introduced into the community, passes it on to 1 additional person, who then passes it on to 1 additional person, et cetera, et cetera, et cetera. We don't have that 1 to 4 to 16. We have 1 to 1 to 1, which is constant incidence. And remember, incidence from 2 is the rate at which new infections are occurring. So we have constant incidence. What if we have more than 75% of the population immune? Well, then we'll have decreasing incidence, which is essentially what we want. It'll be less than 1. We'll have fewer and fewer cases as time proceeds. This concept is great in theory, but there's a few points of caution. The first is that this herd immunity threshold depends upon homogeneous mixing, that members of the population mix at random. we know that that's not true. Our society is so heterogeneous, we call it. We don't mix at random. We are select with the people we're mixing with. And what that means is that it's probably likely that we mix with people who have vaccination or immunity similar to ours. So what that means is that in some population, it's not that the 4 people that each random person will encounter will all be 3/4 immune to the disease. We can't kind of assume this homogeneous mixing, if that makes sense. The other is that this R naught measure is somewhat complicated. It's not necessarily exclusively a characteristic of the agent. It's not necessarily a characteristic of the disease or of the virus. It's really it's better thought of as how the virus transmits within a population. So if you have a population where there's no possibility of transmission, then the R naught could be 0. So R naught is really kind of varies. It's both a characteristic of the virus as well as the context or the environment in which the virus is existing, or where the virus, or in this case, the virus has been introduced. This is from another paper, and the citation is below, and I'm sorry that it's blurry, but what you have on the right-hand side are some basic reproductive numbers for different diseases, and on the left-hand side is the herd immunity threshold. I think this is a really great figure to really drive this concept home. So for influenza A, the R naught is between somewhere around 2 to 4 maybe, and depending on that, you need to reach the threshold theorem around, I don't know, 30% to 70% of the population covered, because we're following this line here. So for rubella, where the basic reproduction number goes from 6 to 11 or something like that, we would need a much greater proportion of the population immunized in order to achieve this threshold. We would need, over 80%. For measles, where the R naught is between 10 and 15 or something like that, we would need almost the entire population immunized in order to reach this constant incidence threshold, which we're trying to get to. So how do we make people non-susceptible? How do we make immunity? How do we create this 3/4 of the population is immune? There's really 2 ways to do it. If you acquire an infection and your immune system will produce antibodies to neutralize the agent, leaving you at least temporarily immune from a new infection. Or you can take a vaccine, which is a biological preparation that provides active and acquired immunity. Herd immunity is so important because let's take the people who have already been infected and can't get immunized. If we're relying on vaccination, why herd immunity is so important as a concept is because a lot of people in our population can't or won't get vaccinated. There's a lot of medical exemptions. You can see them here on the left-hand side. You can be allergic to elements of the vaccine. Your body, you can have a compromised immune system or be on immunosuppressive therapy. Some vaccines aren't eligible for pregnant women. You can be a young baby who is not eligible for a vaccine. Some people don't believe in vaccinations. Some are afraid of side effects, whether that's actual side effects or theorized side effects for which there's no kind of scientific evidence. And there's some religious exemptions that don't really accommodate vaccinations. So a large part of the population won't be vaccinated. So we rely on herd immunity to essentially protect them from becoming infected and from developing and spreading disease. But there's some challenges here, and I just want to end with reiterating the challenges about thinking about herd immunity. The first, we talked about this assumption of homogeneous mixing. The second is that vaccines are imperfect, and they're not necessarily going to convey the same effect for all people. So this assumption that if I'm vaccinated, I cannot spread it to anyone, that's great in theory, but there is some imperfections for a lot of vaccines where there is a likelihood or potential that one could spread it. So we have to think through that. As I said before, vaccination coverage is likely to be non-random, which again, combined with that assumption of homogeneous mixing, is problematic. There's this other kind of thing that happens in communities that as the vaccine coverage increases and we achieve this herd immunity kind of threshold, Some people may decide not to become vaccinated or not to get their children vaccinated and just kind of ride on the waves of the population in which there exists where everyone else is immunized. So they're not going to contribute to kind of the public goal of herd immunity. They're just kind of going to benefit from them. So we see that problem. And if enough people do that, it kind of breaks down our herd immunity as a concept. It's really hard to measure threshold goals. It's really hard to track the population and how many people are immune to a condition versus not. So while the threshold is really important in concept, our public health officials often are striving for 100% coverage among those eligible for it, because it's really hard to track, well, we need 82%. It's really hard to kind of gauge whether 82%, whether we reach, whether that's a target. So often it's just advocated to target 100% of those who are eligible. And then finally, herd immunity is not the same as biological immunization. So essentially it's a probabilistic or a statistical concept. So if you're benefiting from herd immunity, let's say you're in one of those immunocompromised states and you're benefiting from herd immunity, if you move to a region or to an area where that herd immunity isn't present, you're biologically vulnerable from acquiring the infection yourself. So we're not really doing anything biologically to you with herd immunity. We're just kind of reaching statistical thresholds or probabilistic thresholds where the likelihood of you coming in contact with somebody who has the infection is decreased. So that's it for this session. Next, we're going to be talking about how our systems are in place to actually track the spread of disease. I hope this was helpful. As always, stay healthy, stay safe, and stay informed. Thanks.